let's dive into a problem that, let's be honest, drives everyone in the plastics industry crazy. You've got that perfect pigment, right? That vibrant red, but when it comes out of the mold, it just looks dull, or that brilliant white ends up looking kind of yellowish. What is going on? Well, today we're going to solve that mystery.
I mean, this is the big question, isn't it? You use the exact same master batch, the same recipe, but you get a totally different look in polypropylene compared to, say, nylon. It's a constant headache. But the answer? Well, it's actually way simpler than you think. And just understanding it is half the battle.
And boom, there it is. For so long, we've all been obsessing over the pigment, but the real variable, the secret culprit that's been shifting our colors this whole time, it's the polymer itself. You got to remember, every plastic has its own natural character, its own built-in background color that completely changes how we see the pigment inside it.
So that's what we're here to do. We are going to go head-to-head with the 5 usual suspects behind those frustrating color shifts. We're going to get to know their personalities, their little quirks, and most importantly, show you exactly how to get your color right every single time. You ready for this? Let's go!
Okay, before we meet our problem plastics, we got to get the science down. Think of this part as getting our diagnostic toolkit ready. Once you understand these core ideas, you'll be able to troubleshoot pretty much any color variation problem that comes your way. It all really boils down to just 4 things. First, transparency. Is the plastic naturally clear or is it cloudy? Second, melt flow. How does it act when it gets hot and gooey? Third, processing temperature. Just how hot do you have to cook it? And finally, crystallinity. How are its molecules all lined up? Every single one of these has a direct impact on your final color.
You know, the best way to think about this is like an artist. The polymer is your canvas, and the pigment is your paint. So if you're using a transparent canvas, a clear polymer, your paint is going to look super bright and vivid. But if your canvas is opaque or cloudy, it's going to dull that color right down. And if you have a canvas that you have to heat up so much that it gets scorched, well, that's going to change the color of your paint completely. It all comes back to the foundation you start with.
All right, that's enough theory. Let's get our hands dirty. Now we're going to get into the real-world practical stuff. We'll go through our 5 key plastics one by one, and I'll give you the inside scoop on how to handle each of them.
First up is the one you probably see every single day, polypropylene, or PP. We call it the workhorse because, well, it's in everything. And its biggest advantage? It's naturally translucent, which gives it a major leg up when it comes to color. So, because PP is naturally pretty clear, it is fantastic for those really bright, vivid, even neon shades. But it's not perfect. You can run into problems like blooming. That's where additives can kind of sneak out to the surface. And getting a consistent white can be tricky. The key to taming it, as you see here, is using the right grade of titanium dioxide, that's your TiO2, to give yourself a really clean, consistent canvas to work on.
Okay, next up is polyethylene, or PE, and this one is interesting because it's not just one story. It's more like a tale of 2 very different materials, because in the real world, you're mostly dealing with 2 types, LDPE and HDPE. And this slide just says it all, doesn't it? Over on the left, you've got LDPE. It's softer, it's more transparent. That transparency makes colors look lighter, so you can actually use less pigment. But on the right, you have HDPE. It's more rigid and way more opaque. And that cloudiness makes colors look duller, so you have to bump up the pigment to get the same shade. It's a crucial difference. Same color, different dosage.
All right, let's talk about a more sensitive polymer, ABS. People love it because you can get that incredible high gloss finish. But that's exactly why we call it the high maintenance polymer. It gives you a beautiful result, but you've got to treat it just right.
The big challenge with ABS is heat. It needs a really high processing temperature, and that heat makes it want to turn yellow. And that, of course, completely wrecks your whites and pastels. So the solution is a 1-2 punch. First, you have to use highly heat-stable pigments, no shortcuts. And second, you got to shorten the residence time. That's how long the plastic is sitting in the hot machine. The mantra for ABS is get it in and get it out fast.
Okay, on to our next character, nylon, which you'll also hear called polyamide or PA. Now, if you only remember one thing about nylon, make it this. It is the thirsty polymer.
See, nylon is what we call hygroscopic. That's a fancy word that just means it loves to suck moisture right out of the air. If you don't dry it properly before you mold it, you're going to get ugly splay marks and a dull surface. So proper drying isn't a suggestion, it's a rule.
But here's the real kicker. Even after it's molded, it starts soaking up moisture again, and that can actually make the color get darker over time. That's why you absolutely have to condition the final part. Let it sit and stabilize before you sign off on that final color match.
And that brings us to the last one, the premium material in our lineup, Polycarbonate, or PC. Its number one feature, the thing that makes it special, is its unbelievable optical clarity. It really is the king of clarity.
That glass-like transparency gives colors this amazing depth and richness. But PC also processes at one of the highest temperatures of all. And you know what that means? A serious risk of a yellow shift. With PC, there's no room for error. Your pigment selection is absolutely critical. You have to use only the best, top-tier, high-heat-stable pigments if you want to protect that gorgeous clarity.
Okay, we've talked a lot of theory. How about we see this in action? To really make this hit home, we're going to do a simple little experiment. We're going to take one single gray colorant and see what happens when we put it in a few of these different polymers. Seeing is believing, right?
First up, we'll put our gray pigment into our good old workhorse polypropylene. And the result is exactly what you'd hope for. A clean, neutral gray. No surprises. This is our baseline. This is our control.
Now we take that exact same recipe, don't change a thing, and run it in ABS instead. And there it is. See that? A slightly yellowish gray. That's the polymer itself, with its natural tendency to yellow under heat, making its presence known. And for our final test, let's look at that same gray in nylon. The result? It's a noticeably darker, deeper shade. That's a direct result of nylon's own internal structure and properties changing the way we see the color. So there you have it. Same exact pigment, 3 totally different results.
So that little gray test just proves it, right? You absolutely cannot treat all polymers the same. To bring this all home, let's wrap up with a quick rundown of the most common mistakes people make so you can avoid them for good.
Okay, here are the 4 big ones. Number 1, using the same recipe for every polymer. We just saw why that's a disaster. Number 2, ignoring your processing conditions. Remember, temperature and time are color changers. Number 3, forgetting about moisture, especially with our thirsty friend, nylon. And number 4, not making sure your pigment can actually handle the heat. Steer clear of these 4 traps, and trust me, you are way ahead of the game.
So, we've done it. We've decoded the science. We've figured out the personalities of these tricky plastics. The power is officially in your hands now. So the question isn't, why did my color shift anymore? The real question is, now that you've diagnosed the material, how will you master the color?
The missing 50% of exact color matching. Okay? The exact same masterbatch. 3 different rules. Dullness, burn and degradation, mismatch, exactness. Okay? You understand? Knowing your polymer is only half the game. Understanding polymer color behavior secure the first 50% of the match. The kinetic reality. The machine environment introduce massive thermal and kinetic variable that control the final shade. The 4 parameters that final shade: temperature, screw RPM, back pressure, residence time. Okay, you understand? Inside the barrel, simulate stress factor. These factors don't exist in insulation. They generate simulated thermal and shear stress that can permanently alter pigment chemistry. Symptom winners parameter, diagnostic matrix, dull output, burn marks, inconstant hue, temperature, RPM, back pressure, time. Okay, the equation for 100% set control, material foundation, kinetic variable, total set control. Mastering this equation granted constant color output on any machine, whether it's injection molding or extrusion. This what separate operators from true industry experts. System ready for calibration. Accessing model day 13. Objective: deep dive into processing parameter control status pending user confirmation. Like this model, subscribe to CPET Polymer Tech, comment day 13 ready. Thank you.